So I'll wait for a couple of seconds until the live stream starts. Wait. Okay, cool. I can hear myself and I can see the presentation. So I will wait. Okay, cool. People started to show up. So excellent, excellent. So we're going to start very, very, very soon. Just stay tuned. So until we start, I want to wish everybody a happy belated Mardi Gras and happy St. Patty's Day in advance. Okay, cool. So some people are here, so I think it's time to start. All right. So finally, we are here to discuss evolutionary robotics. In the past couple of meetups, we went through modular robots, self-reconfiguration, self-assembly, self-repair, and what else? Self-reproduction classes of modular robotics. Today is a little bit different topic. We're going to discuss evolutionary robotics, so we are going to focus on the software side and the algorithmic side of this science. So let's get started. Before I start, as usual, I want to hear from you. So please contact me if you would like to talk about any project, research, or just something cool you would like to share with the rest of us. We need you, and we want to have you involved. Let's do it together. And also, if you didn't go to archive.org yet, please do so and check my paper that summarizes all our past meetups and share with me your feedback. I want to get your insights and feedback about this paper. So this message is for our YouTube subscribers. Please make sure that you go to our meetup group and join our meetup. Now this message is for our meetup members. Please make sure to subscribe to our YouTube channel in order to get all the links, all the URLs, and all the notifications for our new videos. Ta-da! Let's start seeing our agenda for today. So we will introduce evolutionary robotics, and then we will discuss two papers. The first one is Evolutionary Robotics and Open-Ended Design Automation by Professor Hod Lipson. And then we will go through Evolutionary Robotics tutorial by Nolfi and Floreno. I'm not sure that we will have enough time for both papers because especially the second one is a little bit longer. So we will try to cover as much points as we can in like 30 to 40 minutes. If we don't have enough time, we can finish the second paper in our next meetup in 2 weeks from now. So, what is evolutionary robotics? It is a method for the automatic creation of autonomous robots, which is inspired by the Darwinian principle of selective reproduction of the fittest, captured by evolutionary algorithms. If you guys need to know more about autonomous robots or about evolutionary algorithms, please say something in the chat window here or in the comments part in the meetup website so I can keep track of the topics that you guys are interested in for our next meetups. So the first paper, Evolutionary Robotics and Open-Ended Design Automation by Hod Lipson. In this paper, Professor Lipson introduced systematic synthesis, which is the process of successive adaptation by improvement and recombination of basic building blocks. So this process is open-ended, which is different from classical genetic algorithms. If you guys recall from our first podcast, I introduced a paper that I wrote using genetic algorithms. So this one, the systematic synthesis, follows an open-ended approach, which is different from the genetic algorithms approach that we discussed in our first meetup. So let's see how optimization is different from synthesis. Optimization, we tune the values of a set of parameters in order to maximize the target function. The set of parameters, their meaning, and their ranges are predetermined. So for example, to design a circuit, we manually provide a basic layout of resistors, capacitors, and coils, and then try to automatically tweak their values so as to maximize the performance. But let's see synthesis from the other side, or from another perspective. Synthesis is an open-ended process where we can add more and more components, possibly each with their own set of parameters. So now, if we want to design a circuit, again, we could start with a bucket of components and use an algorithm to automatically compose them into a circuit that performs the target function. So here, the algorithm will design the circuit for us in the synthesis part. However, in the optimization part, we manually provide the basic layout of the circuit components. A simple model of evolutionary adaptation. So evolutionary process starts with an initial population, which is a large set of initial candidate designs. And then after performing repeated selection and variation processes, we will get the final result. But first, what is selection and variation? Selection is performed by measuring the performance or fitness of each solution in the population. Make sure that the fitness metric needs to be solution neutral, which means that it can measure the extent to which the target task has been achieved, regardless of how it was achieved. So, after we measure the fitness, we select the better solutions. We call them parents, and then use the parents to create a new generation of solutions, and that's we call offspring. So the offspring are variations of the parents created through variation operators, such as mutation and recombination. So again, the process is repeated generation after generation until good solutions are found. Robot body and brain. That's similar also to the contents of our first meetup. So each robot has body and brain. The body can be referred to as morphology or hardware, while the brain is the controller or the software. In evolutionary robotics, the majority of the time, researchers focus on evolving controller while keeping the morphology fixed. But other researchers work on evolving both bodies and brains. So with design automation, we could reverse engineer the evolved controller to find out exactly how it works, if you're interested in knowing how these solutions came out. So how can we represent the morphology of a robot? By using either tree representation, developmental representation, or regulatory network representations. So tree representation, a set of operations to construct a phenotype in a top-down or bottom-up manner. So this diagram here represents the top-down representation. So the top-down tree representation starts with an initial structure or an embryo and specifies a sequence of operations that progressively modify it into its final form. But the bottom-up construction of 1 degree of freedom mechanism begins at the leaves. As the name suggests, of course, it begins at the leaves of the tree with atomic building blocks and hierarchically assembles them into components. So how could a tree representation be used to describe robot morphologies? Top-down construction of a mechanism starts with an embryonic kinematic basis with the desired number of degrees of freedom. A tree operator then recursively modifies that mechanism by replacing single links. Each link has a DOF of -1, with assemblies of links with an equivalent DOF, so that the total number of degrees of freedom remains unchanged. So what about developmental representation? It allows the robot's morphology to develop from a basic seed and a set of context-free development rules. There's something called an L system, which is a set of rules, like the A leads to B and B leads to AB. These rules are parametric. They may pass parameters and have conditions. So these are executed only when the parameters meet some conditions. An evolutionary algorithm was used to evolve individual L systems that, when executed, produced the build sequence which produced the machine. So the last representation is the regulatory network. So robot elements such as actuators, sensors, are connected through a neural network, but the specific connectivity of the network is determined by an evolved regulatory network. I hope that makes sense. So let's talk about evolving machines in physical reality. Evolving controllers for physical morphologies. In order to make a perfect simulator, that whatever works in simulation will work in reality equally well. That's a little bit hard. To use a crude simulator that captures the salient features of the search space. So you can co-evolve simulators so that they are increasingly predictive. And there are two phases to do that. Exploration phase, which is evolving the controller, and estimation phase, which is creating the simulator. So that actually leads us to what? Reality gap. So if you guys heard something about reality gap, please share it with us in the live chat tab. I will give you like a minute or two because there is a delay. And then after reading your comments, we will move to the next slide. So I'm unable to connect to chat. That's why, let me just say something here. Okay, it worked. So I'll start by discussing the reality gap until I hear from you. So the reality gap is that you design a robot in simulation and it works perfectly. But once you decide to implement this robot physically, now it's not gonna work as good as it did in simulation. So that's what we call reality gap. And it's a big problem in this field. Okay, let's keep going. Making morphological changes in hardware. Oh, we have what? Reconfigurable robots. We talked about them many times in our past few meetups. Reconfigurable robots are composed of many modules that can be connected, disconnected, and rearranged in various topologies to create machines with variable body plans. The self-reconfigurable robots are able to rearrange their own morphology and thus adapt in physical reality, producing the entire robot morphology automatically using 3D printers. The printer, when coupled to an evolutionary design process, can produce complex geometries that are difficult to produce using any other way, and thus allow the evolutionary search much greater design flexibility. It's going to be awesome if it's implemented in the right way. So that was all for our first paper. And I think we have 10 to 15 minutes to cover the next paper, which is an evolutionary robotics tutorial by Stefano Nolfi and Dario Floreno. And the next slides were made by Nolfi and Floreno. So I took these slides from their website, and we're going to discuss them together because they did a great job. And I felt that there is no need to recreate these slides to summarize their own paper. No more questions before we go to the new paper? Okay, I think we're good, so let's start. The method of evolutionary robotics is the attempt to develop robots and their control systems through an automatic design process involving artificial evolution. So the basic idea behind evolutionary robotics is the following. An initial population of different genotypes, each codifying the control system and sometimes the morphology of a robot, are created randomly. Then each genotype is translated into the corresponding phenotype and tested in the environment for its ability to perform a desired task. After that, the robots that have obtained the highest fitness are allowed to reproduce by generating copies of their genotypes with the addition of changes introduced by some generic operators, such as mutations and duplication. The process is repeated for a certain number of generations until the desired performance is achieved. All of this is similar to what Hodlipson went through in his research paper, and we covered earlier. But I think that Nolfi and Floreno focused more on the genotype and phenotype, and also the fitness function. They mentioned that the experimenter designed the fitness function that is used to measure how much an individual robot is able to accomplish the desired task. Also, the designer usually specifies how genetic information are translated into the corresponding phenotype. The mapping between the genotype and phenotype is usually task independent, and as a result, they evolve behaviors, and the way in which behaviors are produced are largely the results of a self-organization process. So we can say that this approach shares many of its characteristics with other related approaches, such as the behavior-based robotics, which is based upon the idea of providing the robot with a hierarchically organized set of sensory motor processes and letting the environment to determine which behaviors should have control at any given time. In this approach, as well as evolutionary robotics, the environment has a central role. In particular, the environmental conditions determine which behavior is active at any given time. Also, robots are usually designed in an incremental fashion through a trial and error process in which the designer adds a new higher level layer only after testing and debugging the behavior resulting from the lower layers in environment. Evolutionary robotics, by relying on an automatic evaluation process, usually makes a much wider use of this trial and error process. Sounds good. Move to the next slide. All right. Learning robotics, NER. Other related approaches are based on learning. The idea is that a control system, which is typically a neural network, can be trained using incomplete data and then allowed to rely on its ability to generalize the acquired knowledge to novel circumstances. The researcher, in this case, should provide to the learning network a feedback that may be the desired state of the actuators each time step, or a reinforcement signal indicating how good or bad the network is doing time to time. Evolutionary robotics shares the emphasis on self-organization with this approach. Artificial evolution may be desired as a form of learning in this case. Artificial life and evolutionary robotics. Artificial life represents an attempt to understand all life phenomena through their reproduction in artificial systems, typically through simulation. Evolutionary robotics shares many characteristics with artificial life, but it also stresses the importance of using a physical body such as a robot instead of a simulated agent. In the top part of the slide, you can see a typical example of an artificial life experiment in which the environment is represented by a two-dimensional grid of cells in which sensors have infinite precision. In the bottom part, you can see an example of an evolutionary robotics experiment in which the training is accomplished by downloading the genotype of each individual for each generation into a real mobile robot. Okay, so we talked about evolutionary robotics for maybe 26 minutes now. But how to evolve robots? The most straightforward way to evolve robots is to do it in the real environment, which is a good way to bridge the reality gap that we talked about earlier. In this slide, you can see two competing populations of robots, predator and prey, are evolved in the real environment. The robots consist of two Kepra robots with different sensory motor structures, as you can see on the left side of the slide. During the evolutionary process, each individual of the evolving population is embodied in the real robotic body and tested in real environment. For this reason, the evolutionary process can require a rather long time. Another possibility is to evolve robots in simulation and then test the evolved robot on real environment. This way can significantly reduce the time required to perform an experiment. So in order to be effective, this way requires that all the relevant aspects of the robot, the environment, and the robot environment interaction are accurately modeled in the simulation. Otherwise, the evolved robots will stop to work once transferred into the real environment. Evolution in the real world. In order to evolve robots in real environment, we need to consider some issues. Number one, mechanical robustness. Number two, energy supply. And three, analysis. So mechanical robustness. During the evolutionary process, and especially in early generations, individuals may produce behaviors that can be damaging for the robot hardware, such as high-speed collisions against objects or sustained strong currents to motors pushing towards a wall. So in order to solve this problem, you can use small robots. Another issue is energy supply. Evolutionary experiments last longer than the average battery duration. For this reason, it is necessary to provide the robot with an ability to autonomously recharge its batteries or bypass this problem in other ways. One possibility is to use a thin cable with rotating contacts, like the one shown in the middle picture. This technique allows to save the time required for periodically recharging the batteries, and it also supports data communication with a host computer. So it allows storing large amount of data that can be used later to analyze the evolutionary experiment. So the last issue is the analysis of the evolved behavior and of the evolutionary course. So, evolution in simulation. In order to accurately model robot environment interactions, every researcher must face some problems. One of these problems happen because different physical sensors and actuators, even if they look identical, may perform differently because of slight differences in their electronics or mechanics. I'm not going to talk more about evolution in simulation because this is, a big topic. And I prefer to start our next meetup in 2 weeks from now with evolution in simulation. And then we can continue this presentation, which was, as I mentioned earlier, done by Nolfi and Floriano. So we can go through designing the fitness function and genetic encoding. And then we will keep going. So, if you guys have any questions, please use the live chat. We have 2 minutes to wrap up. And I would like to hear from you. So I saw more interaction from you guys in the past couple of meetups where we discussed hardware and we went through different applications. I know this might be considered as the dry topic compared to our previous topics, but I want to hear from you. Let me know what kind of presentation you prefer and what kinds of topics do you like to learn more about. I think everything is good. And I think also that there was a problem with live chat because there is like a small error message that I can see here. Not able to connect to chat, and the only message that I can see is my own message. So hopefully by next week this problem is going to be solved. Anyways, if you have any comments and this live chat tab didn't work, please go to our meetup group and mention them there, and I'll be happy to reply to your questions over there. So thank you very much for your time and for listening and for staying here the whole time of the meetup or the podcast. And I wish you a great rest of day and rest of week. And see you again in 2 weeks. Bye-bye.